The purpose of this video is going to be to talk about how current divides in a multi-branch circuit. I have here a circuit that's a little more complicated than previous ones you've seen. It's not a series or a parallel, it's kind of a combination of both. Let me show you. If we take out paths that current could go by, it could leave the positive terminal, go through the 100, go down through the 4700 in this meter, through this meter in the 22, and get back to where it started. However, it could also use that outer branch. Could go through the 100, skip the 4700, go through the 1000 and this meter, then it has to go back through that 22 again before it gets back home. So in a very real sense, the 100 and the 22 are different than the other two resistors. The 4700 and the 1000 are in parallel with each other, but the 100 and the 22 are in series with both of them and each other. So what's the relationship between these currents? I think it's worth checking, and that will help us understand Kirchhoff's junction rule, which is one of the most powerful tools in helping us understand circuits. So because we're measuring currents, we actually have to break the circuit because you measure current through. So I'm going to pull out the 4700. I'm going to disconnect it from the top of the circuit. I'm going to hook one of the yellow wires where it used to be, hook another up to it. So now if I put the ammeter in, I can measure current through it. We'll flip that so it's in the right direction. We get a current through the 4700 ohm resistor of 276 microamps. So I'll write that down. I already forgot it. 276. So 276 mu amps. And now we'll go through the 1000, so we have to put the circuit back together. 4700 goes back like it used to be. And we'll pull the 1000 out. Put a yellow wire where it should be, yellow wire to it. We'll get its current. 1211 microamps. So now all that remains is to get the current through the bottom here and through the 22 ohm resistor. So we'll put the 1000 back together. Make sure everybody's seated well. We'll pull off the 22, give it a new home. Yellow wire up to it, yellow wire up to these two guys. Excuse me. And we'll get the current through the 22. We get 1431. So if we look, there's a fairly clear relationship between these currents. If we simply add them together, 1211, 276, we should get something very, very close. So we should be getting 1487 microamps. We're getting 1431. These are very, very small currents, so the meter's not super accurate. But I think it makes intuitive sense that the current through the entire circuit, which represented by the 22 ohm resistor, would be the sum of the currents through the two separate branches. So that brings us to the definition of Kirchhoff's junction rule. He says if you have a junction, like right here, and you have currents coming into it, you have to have the same current going out of it. It's a statement of conservation of charge. Charge doesn't get lost. So we've got 1450-ish milliamps coming in through these two branches. We've got 1450-ish microamps coming out. No charge is lost in there.